All right, good morning, ladies and gentlemen. Week 10. Roar! Okay, almost done. Last week of classes. No homeworks or anything left for this class. All you got to do is take exams. The easy part, right? Right. Okay. Um, so announcements. I did release homework number 8, which is fatigue. That stuff in that homework won't be on the exam for this week, but I will have a fatigue question on the final. Okay, so be ready for that. Exam 2 practice problems were released with full solution, so hopefully you've had a chance to at least maybe take a look at those. We're going to have a review session tonight, 7 o'clock p.m. on Teams for those interested in kind of going over some of those practice problems. It'll be pretty similar to what we did last time, okay? Kind of pick one from each section and go through it and work our way through those problems, okay? And then your exam 2 for this class is this week during the lab. All right, so that's what we got going on. And this calculator meme specifically for this week. All right, so trust issues with yourself. I do this all the time too, even when I'm making up exams, making up homeworks, etc. 3 plus 7, better go to the calculator. Okay, that's how I feel about it. All right, so let's continue with the fatigue notes and pick up where we left off. Go away. Okay. Back to reality. Oops, there goes gravity. All right, so back to fatigue. All right, so kind of pick up where we left off. We were talking about modifications to the endurance limit. All right, and the basic idea is that we have a modified endurance limit we called SE, which is going to be modified in this class by a couple of factors. One for the surface roughness, so we say here this is a constant C surf. Okay, very Hawaiian. Another modification that we have is for size, C size. Another modification that we have is for load. So these are the three that we're going to talk about, and these are all modifying the pristine endurance limit, which we call SE prime. So remember this SE prime limit, this is pristine endurance limit, and this is obtained from the RR Moore high-speed test and can be calculated using the ultimate tensile strength. All right, so just a reminder of what that looks like. We kind of have this chart in your equation sheet that sort of tells you how to calculate the pristine endurance limit given various ultimate tensile strengths of certain materials. Remember, this is all based on experiment, so it's all empirical. But this is on your equation sheet, okay? So that's how we get the pristine endurance limit, and now we have to modify that pristine value for certain characteristics, including the surface roughness, the size of the piece, and the loading type that we have. So last time we talked about how to modify for surface roughness, and we said that this was equal to A SUT to the B, where these constants A and B are given based on experiment again. Depending on the surface roughness of the piece, the more rough the piece is, the higher likelihood you will encounter a flaw, which reduces your endurance limit. So the constants A and B come from a chart that looks something like this, which is also in your equation sheet. So if you need to modify the pristine endurance limit for some surface characteristics that you might have, this is the chart that you want to go to. Where we left off, we were looking at size modification. And so this is where we left off. And we had discussed size modification in two different kind of loading scenarios. One was for rotating bending, one was for non-rotating bending. Okay, so this is size modification. Okay, and so I'm not going to beat this to death. I just want to kind of give the highlights here quickly because we talked about this in the last lecture. Is that the size correction is more or less given by a series of tables that are also in your equation sheet that look something like this. right? So this is in your equation sheet here. The idea is you have some size modification factor we call C size that depends on the geometry and the loading character of your piece. All right, so more or less it's given by these sort of equations that you see here. And whether you're in metric or in English units, and depending on sort of the size of the hydraulic diameter that you have or the effective diameter that you have, you're falling in different regions. So here the D's that appear inside of these equations are the effective diameters of the pieces. And the effective diameter is sort of calculated using this equation over here, which is a statistical calculation based on the cross-section of the piece using this A95 variable. So we kind of went over this, but this A95 variable is a representation of a statistical size of the cross-section given various cross-sectional types. So we could have a circular cross-section, could have a square cross-section, here's an I-beam, here's a C-channel. All right. So it tells you in this chart how to calculate A95, and calculating A95 depends on if you're in a non-rotating or a rotating sort of loading configuration. These rotating and non-rotating really only applies to bending. All right. It's really hard to have like a rotating axial load. I don't even know how you do that. No, that doesn't make any sense. Okay, so non-rotating is usually what you want to kind of go with. All right, so this is about where we left off. I wanted to do one example quickly using the size modification. We had kind of beaten the size modification theory to death, and so I wanted to do an example problem before we move on to the next size correction or the next correction factor, which is the loading correction factor. So here, let's do an example. This example is, again, just coming right from the notes. I think this is slide 11. Yeah, slide 11. All right, so pristine steel shaft, 32 millimeters in diameter, with an ultimate tensile strength, SUT, 690 MPa. All right, so pristine, this word is important here. It's telling us that the surface of the material is well polished. It's pristine, so not ground or hot rolled or forged or anything like that. So we don't have any surface modification that we need to make. All right, so here we have an ultimate tensile strength of 690 MPa. We're asked to find the modified endurance limit in two situations. A, if loaded in rotating mode, and B, the non-rotating mode. Okay, so remember what each one of these looks like. I just want to draw a quick sketch here to remind ourselves. The rotating mode is something like this, where we put this guy into 4-point bend. And this is spinning with some motor. Okay, in this rotating mode, every single point on the outside of the cross-section is feeling the maximum tension and compression. A non-rotating mode, you basically have the same sample geometry. Okay, except now it's not like rotating in a constant 4-point bend, but here we're just kind of applying sort of this like cyclic sort of bending that looks something like this. All right, in this non-rotating mode, only the top and the bottom points on that cross section are experiencing the maximum tension and compression. Okay, so with this situation, which one would we expect to have a lower endurance limit? Anyone in the class? Rotating. Explain why. Right, you have a higher likelihood of fully loading a flaw on the surface of the material. That's probably the best explanation. Okay, so the probability of loading a flaw on the surface is much higher if you're in the rotating mode, because every single point on the outside of the cross section is experiencing the maximum tension and compression. So we would expect this to be lower. All right. Hopefully our math shows that to be true. Otherwise, I will retire at the ripe age of 33. No, I don't got enough money for that. Okay. Maybe I'll go out and buy a bunch of lottery tickets. No, I won't do that because I understand basic math. Okay. So let's work through this. All right. So here we have, we want to find an endurance limit. And, you know, the first step that we have to do when we go through this is to determine what the pristine endurance limit is, and then modify that appropriately. So we'll use that our modified endurance limit is equal to, we're just modifying here for size times the pristine endurance limit. We may also consider modifying for surface, but we're told in the problem that this is pristine, so this is going to be equal to 1 because this is pristine. So we're not going to modify at all for the surface because we're told in the problem that it has this pristine, highly polished surface where we don't have to worry as much about flaws occurring. Okay. So step number 1 then is determining this pristine endurance limit. Okay. And to do this, I can use the chart that tells me what the pristine endurance limit is given the ultimate tensile strength. All right. So here's the chart from your equation sheet. We're told we have a steel shaft with an ultimate tensile strength of 690 MPa. Okay, so here, this is kind of the condition that we have, an ultimate tensile strength less than in metric 1460 MPa. So this will allow me to calculate my pristine endurance limit as 0.504 times the ultimate tensile strength. All right. So here, told it's 690 MPa. And so my pristine endurance limit for this particular problem, 348 MPa. Okay, this is my pristine endurance limit. I haven't modified for size in any way yet. Okay. This comes from the RR Moore test. If I did the RR Moore test on this particular piece, I would expect an endurance limit of 348 MPa. So now I need to modify for size. And we're asked about 2 different conditions. One, the rotating mode, and the non-rotating mode. So let's first start with the rotating mode. Okay. We know that we need to use this chart that sort of tells us which mode that we're in and which size of our cross section we have. Sorry, I got some program running in the background here that's kind of annoying me. Go away. Okay. So what we want to do is we want to look at our size correction factor. And that, again, is in your equation sheet, and it looks something like this. All right. So this particular problem, we have a circular cross section, and we're going to investigate the non-rotating and the rotating modes. So we're going to have 2 values for this A95 that go into calculating the effective diameter of this piece based on the type of loading. So we're first looking at the rotating bending mode. So let's attack that. We'll see that this A95 variable, which feeds into the diameter, is going to be 0.0766 times the diameter of the shaft squared. So that's what we're going to go with here. So here, this A95 variable is equal to 0.0766 d squared. So here this is 0.0766. I'll work in millimeters. We're told the diameter of the shaft is 32 millimeters. This is 32 millimeters squared. Or I'll have here that this A95 variable is kind of the first one that we need to calculate. 78.44 millimeters squared. So now this gets fed into this equation for the effective diameter here. Whoa, baby, what happened? Sometimes it just like makes these massive jumps. I haven't like gotten the touchdown yet. And neither have the Dallas Cowboys. Oh! Okay. So then, the effective diameter. No, just kidding. They got a couple yesterday. They still lost. This is this A95 variable divided by 0.0766. Lo and behold, because of the way that the rotating bending mode works, these will cancel each other out, and you're just going to end up with the original diameter of the piece. It's 32 millimeters. So when you're in the rotating mode, the effective diameter is the diameter of the circular piece. All right, so here's my effective diameter for calculation. All right. Then I go to my chart, and I look at where does this effective diameter fall, kind of in the range of calculating C size. All right, so here we're falling in this range. The diameter is between 2.79 and 51 millimeters, because we're at 32 millimeters. So I need to use this general formulation to calculate C size. 1.24 d to the negative 0.107. Again, just an empirical value that just happens to fit well with the data. Yeah, this is 1.24 times the effective diameter to the negative 0.107. All right, so 1.24. And here we're using effective diameter in millimeters. It's not really stated well in the chart, but you need to use millimeters here for this calculation to work. So our size modification in this particular situation is going to be 0.856. All right. So because of the difference of the size of this piece compared to that which is typically used in the RR more high-speed test, which I think is 1 inch in diameter, we have to modify the pristine endurance limit by 85.6%. So here, I'll say SE for rotating, because that's kind of what we're doing here. Size modification, 0.856 times our pristine endurance limit, which we calculated before, 348 MPa. And we'll have here that the endurance limit in the rotating mode, 298 MPa. All right, so here's our answer for sort of the first part of the problem. Part A for calculating the endurance limit in the rotating mode. All right. So we can move on to the non-rotating mode, and the method of attack is still the same. We still need to calculate that A95 variable. But here it's going to be different because we're in the non-rotating mode. Again, it's like this kind of strange, bouncing back and forth kind of bending mode instead of that full rotating mode. Right? So here in the non-rotating mode, we'll see we have a different sort of coefficient in front of the d squared, 0.010462. Very precise. Apparently they can get it to that precision, which, suspicious. As they say in Among Us, very sus. All right. So here this A95 is 0.010462 d squared. Okay. 0.10462. Diameter of my shaft, 32 millimeters squared. So this 8095 variable here, in this case, 10.71 millimeters squared. All right. This feeds into the effective diameter calculation, which we've already seen. 10.71 millimeters squared over this 0.0766 constant value. And in this non-rotating situation, I get an effective diameter here, which is markedly different, 11.82 millimeters. So in this non-rotating mode, we generally have a significantly lower effective diameter. That's basically telling us that we have less area over which to concern ourselves with flaws. All right. All right. So our effective diameter, 11.82. We go back to the chart. We see where that effective diameter fits in on our appropriate domain. And so again, since we're at this range between 2.79 and 51 millimeters, we're still going to use that 1.24 d to the negative 0.107. But my effective diameter here is now just a different value. Still this 1.24, effective diameter to the negative 0.107. So here this is going to be 1.24, except now my effective diameter is 11.82 millimeters to negative 0.107. And so for the non-rotating mode, my size correction factor is different, 0.952. Okay. So finally, my modified endurance limit, given this non-rotating mode, I'll say NR, non-rotating, is going to be this new size correction factor for the non-rotating mode, which is 0.952, multiplied by the original pristine endurance limit, which was 348 MPa, or here that we'll have the non-rotating endurance limit, 331 MPa. Okay, so notice here in the non-rotating mode, 331 MPa is our modified endurance limit, and this is higher than that we saw for the rotating mode. So here, 331 MPa for non-rotating. Compare that to 298 MPa for the rotating bending mode. Okay, and again, it's because the rotating bending mode, every single point is exposed to the maximum and minimum stress. But in the non-rotating mode, it's just the points on the top and the bottom, and points near to the top and the bottom, which are experiencing that maximum stress. All right, so there's your size correction factor. Next, let's look at correcting for loads appropriately. The last thing we're going to do is load correction factor. This one is easy. Save the best for last, I tell you. So we'll remind you that the RR Moore test is tested in rotating bending. Okay. We need some sort of methodology to account for other types of loading. Okay. So endurance limits with other loading types differ. Okay. And by other loading types, I mean like pure axial fatigue, right? Axial fatigue is kind of like something like this, right? Or pure torsional fatigue, which is something like, okay, so we'll say And this is pretty straightforward. You just multiply it by a constant. Again, these values in your equation sheet, and just look like this. For bending, your load modification is 1 because our more isn't bending, so you don't need to modify by anything. Okay. If you have axial fatigue loading, you modify your pristine value by 85%. And interestingly, in pure torsional fatigue, you modify by about 60%. Here, 59%. This here is interesting because we know the max shear criteria uses like a factor of 2. It should be like a factor of 0.5. And so when you're putting something into pure torsional stresses, you have basically a pure shear situation going on, and you're modifying by about 50%, just like you do for max shear criteria. So not unreasonable to see a 60% modification for a pure torsional loading. All right. This doesn't come up all that often, but could in situations with multiple loading types. Ay. Hiya. So if you're, for instance, somehow in axial and torsion at the same time, could happen. Washing machine style. Okay. um, use largest modification factor. Okay. So what I mean by that is if you have like axial and torsion, that would be like this sort of situation going on here. Axial and torsion at the same time. Use the largest value, which would be that of the axial loading. Okay. No example problem here. I think this is pretty easy to handle. Right. Okay, let us continue on with the last sort of bits of material here for this portion of the class. One thing we haven't talked about yet that comes up often for fatigue loading is the idea of stress concentration. So everything we've talked about right now has been nice rounded edges and perfectly square, perfectly circular cross sections with no stress concentrations. However, we know that in the real world, stress concentrations exist and will amplify stresses. And how do we deal with that in fatigue? Well, in fatigue, stress concentrations work slightly differently than they do in static conditions. So let's kind of review or recall what a static stress concentration factor is, and then we'll talk about how we modify for fatigue. Okay? So let's review static stress concentration factors. You guys talked about stress concentration. Did you talk about stress concentration factors? 2004? Yes? No? Really? Like, what is the amplified stress around a hole if you load a plate? Yeah, okay, God. Now I'm getting like all the, now I'm getting, oh, yeah, okay, no, yeah. But did you not call them stress concentration? What did you call it? Like stress amplification or something? Yeah, okay. Well, let's review because we seem to know it so well. All right. So, an example, plate with hole. This is like the, key prime example of stress concentrations. All right. So let's say that you're loading this particular plate with some far field stress. Let's call it sigma 0. The stress around the hole gets amplified by some certain value. And we call that amplification factor the stress concentration factor, usually given KT. Sometimes it has some other values. But here, the stress is going to be amplified, and it'll be KT times sigma 0 equals sigma hole. Let's say the stress around the hole. All right. This KT value here, this is called the stress concentration factor. All right. In this particular situation, the maximum value the KT could take is the value of 3. It's kind of a known theoretical solution. But there are charts and tables that exist in the backs of books everywhere that basically tell you, all right, if my plate is this wide and my hole is this big, what is the amplification factor around the hole? Okay. And there are tables for this stress concentration factor, KT, that look like this guy. This is in the back of your Shigley book. Okay, sorry for the blurriness. It's the best I could do. But here, this is your stress concentration factor on the y-axis, and given various dimensions of the plate, so here your plate is some width W, and your hole has some diameter D. If, let's say, the diameter of your hole is 50% of the width, then your stress concentration factor here is like 2.15, something-ish, okay? So you would amplify the stress by a value of 2.15 around the hole to calculate what the actual stress around that hole is. The amplified stress, the stress concentration around that particular hole. So this is for one particular type of loading. This is obviously for like axial load in a plate with a circular hole. This is one specific loading type. And these charts that you see are usually for static conditions. Static. Right? Meaning if I was just like pulling it in one direction. Okay, generally what this looks like equation-wise is you might see this as KT is whatever the maximum value is around your amplified stress region, so sigma max over sigma naught, where sigma naught's the far field applied stress. Or you might see KTS, which is the shear stress concentration factor, is the maximum shear stress divided by the far field shear. So this here is for normal stress. This is for shear stress. So obviously this chart that I showed up here, this is a normal stress situation here, obviously. A shear stress situation might look something like you have some round bar. Okay, and here you've got a notch in it. Okay, so here this is a notch. And we're putting this thing into torsion. This would be like a situation where we'd have a shear stress amplification because of like that notch that exists kind of around the center of that particular piece. All right, so that's a situation where you might see that happening. Okay, so these factors exist, and they exist in lots of charts and tables that you can find in a variety of resources, your book, for instance. All right, that's for static conditions. We want to have some stress amplification factor, some stress concentration factor that works the same way but with fatigue. So that's the static conditions. Let's talk about fatigue. Okay? The idea is very much the same, that you have some intensity of stress around some discontinuity in the piece, and we're going to amplify the stress around that region using some factor. However, the factors now are different. So same idea, different factors. Okay? Mathematically, we don't use KT anymore. We use KF. And the idea is still the same. The max stress divided by far field stress. Oh, let's leave this is going to be the max divided by actually the amplitude of the stress. It's applied far field. Similar idea in shear. This is KFS. This is going to be the maximum shear that we experience in fatigue divided by the shear stress amplitude, tau A. Stress amplitude here. That's a normal stress, and here we have a shear stress amplitude. This is fatigue concentration factor. This here also fatigue concentration factor. But this is specifically for shear. Okay. These are both calculated using static concentration factors with a twist. So they're calculated using these particular values. With an additional twist. Okay. The twist is what's called the notch sensitivity factor. The twist. It's like a horror film. What's around the corner? Oh, it's the notch sensitivity factor. Oh. We're past Halloween now. Okay. Next Halloween, I'm gonna make a scary movie called Notch Sensitivity Factor. And the notch sensitivity factor are given the variables Q for normal stress and QS for shear stress. So normal and shear. Okay. So finally, we can give you the form of KF and KFS. the fatigue concentration factor is 1 plus Q times KT minus 1. KFS 1 plus Q times, sorry, QS times KTS minus 1. These are how we calculate fatigue stress concentration factors. All right, there are charts. For Q and QS. Gosh, my Q's today. What are you accusing me of? Okay. There are charts for Q and QS, also in your equation sheet. What a shock. Here's the idea. You have some fatigue setup. All right, you've got a plate with a hole in it, and you're doing this thing to it. Okay, you go to the charts that would give you that stress concentration factor for the static condition. Okay, that would afford you something like KT. We talked about this before. If you had a plate with the width that was twice the diameter of the hole, then your static stress concentration factor was about 2.2. We saw that in the chart before I talked about it. Okay, so that's where you get that value. Then you go to this notch sensitivity chart to figure out the value of Q. Plug all that in, and you can figure out your fatigue concentration factor. All right, so what do these charts actually look like? Okay, these are given in the notes. This is page 15 of the notes. Otherwise, these charts are also in your equation sheet. All right, so here we are. Here's your notch sensitivity on the y-axis. Here's for Q, here's for QS, or what they call in this table Q shear. Same difference. The idea here is that you find the line that is closest to your material with the tensile strength. All right, so here these black lines are for steel. So if I have a steel with an ultimate tensile strength of 150 KSI, I'm looking at this line here. Right? I look at my particular piece, and I look at the radius of the notch inside of my piece. Okay, if I'm talking about that bit and torsion, I'm just looking at the notched bit. If I'm talking about a circular hole inside of a plate, what's the radius of that circular hole? Okay, that's the notch radius. Okay, given in millimeters on the top, inches on the bottom. Okay. So here we go. Let's say I have a radius, I have a circular hole inside my piece that's 6 millimeters. All right, well, my radius of that hole is 3 millimeters. And so I come to my chart and I look at, all right, my value of Q, if my ultimate tensile strength for this piece happens to be 150, is right about here. That gives me a value of Q somewhere in the 0.9 range, somewhere about there. All right, so I take my notch sensitivity value as about 0.9 in that situation, just giving you an example. All right, let's say I have a steel with an ultimate tensile strength of 60 KSI, and I have a very small radius hole. All right, 1 millimeter. All right, so I come into my chart here. I'm taking off this value, which is about 0.67-ish. Okay, something like that. So you get the general idea. This is how we're calculating notch sensitivity, given radius of the hole, ultimate tensile strength of, in this situation, steel, but we also have a line here for aluminum alloys, and that is independent of the ultimate tensile strength, but you get the general idea. So this is for normal stress notch sensitivity. Here's for shear stress notch sensitivity. All right, two different charts. Make sure you're using the right one. Okay. Yeah, we got time for the last little bit here. Okay, so that's how we calculate concentrations in fatigue. So remember, when you're doing fatigue, you're not just looking at the static value. You have to do one more modification based on this notch sensitivity factor. Okay, so that's that. All right, the last thing that we want to do, all we've talked about so far is estimating endurance limit, right? We might find it more useful to actually estimate number of cycles to failure given some situation. All right. Actually, I'm going to save this topic for Wednesday. This is a little bit intense. So we'll stop today. When we come back, we'll talk about how to estimate cycles to failure. That's it for today. I don't want to rush through this. This is kind of a long topic. That's it for today. See you on Wednesday, or see you tonight. Don't forget review session, 7 o'clock in my living room. All right. Or your living room, or whatever. You know, you get the point. Come join us.